Hi, everyone. Now handing over to Adam, who's going to be talking about breaking into blockchain for fun and profit. Adam, over to you.
Thanks, Hassan. So hello, I'm Adam Englander. I am the Director of Engineering at ZettaFi Labs. And I work with an amazing team of engineers who are looking to make blockchain data, and any other data for that matter, available in a decentralized and easy-to-use manner. So blockchains are treasure troves of data that are free and open for anyone to utilize. A lot of the talks today have been kind of focused on that. So whether you're looking to analyze game NFTs or see which items are most popular, tracking gas prices for transactions, or looking to analyze trade positions on cryptocurrency exchanges, you'll need to know where the data is and how to get it. So let's start breaking into the blockchain. This is a 15-minute presentation. My goal is not to teach you how to do things, although there'll be examples. My goal is to try and demystify how the blockchain stores data and how to get that data with Python applications using just the API and some helper libraries. Some of you may be using Web3 to access Ethereum blockchain data, and this presentation will give you some insight into what it's doing behind the scenes. It's also helpful when it doesn't do what you expect it to do, and there's no quick answer when you do a little Google search. All the presentation will be specific to Ethereum and Ethereum-based blockchains like Polygon, Avalanche, Binance, etc. Many of the concepts apply to non-Ethereum blockchains, but we're going to specifically talk about Ethereum. And I'm going to move really quickly through the presentation. A link to the presentation will be made available at the end if you'd like to review some of the examples. So blockchain data contains all the historical information for every event that occurred within it. It stores the data for validation and replication. You and I can use that data for whatever we like. First, we need to understand the data and how to retrieve it. So aside from all the information used to create and operate the trustless system, blocks are sequential data containers with transaction and event logs. Blocks contain more than just transactions. The most important data that I use that I find in the block is the timestamp. This is the only link between the blockchain and actual time. Transactions keep the who, what, and how much of the blockchain. So it records transfers of cryptocurrency, creation of smart contracts, and the execution of smart contract functions, along with other pieces as well. Logs contain events emitted by smart contracts. These events are point-in-time views into actions in a transaction. One example would be a transfer event for an ERC20 or ERC721 smart contract. While the contract can tell you who currently owns the token, the events in the logs can tell you the entire history of ownership for that token. So now that we have a high-level picture of how the data is structured, let's look at how to access the data using RPC, or JSON-RPC 2.0 to be more specific. It's used interchangeably, and oftentimes it's called RPC, which gets people super confused because RPC is actually just kind of a general term. So it's how we talk to the blockchain. RPC is just a structured data definition for sending requests and receiving responses. You have requests in which you send methods and parameters and receive a response with a result or an error. Here's an example of a fairly simple RPC request and response. The method is block number, which retrieves the current block height. There are no parameters, so they're omitted. The result at this time, when you decode the hex, is 15,818,914. Errors are pretty self-explanatory. Check the spec for deciphering the codes. If you're using HTTP as a transport, you may want to utilize batch requests to reduce overhead of request latency. You've probably heard this in other talks. A batch request is just JSON array of request objects, and a batch response is just JSON array of response objects. But this is where when you make it every request, you're going to send along an ID. Sometimes they don't matter. In batches, they do if you want to be able to match up the responses to the requests. You'll also want that if you're using if you're not using HTTP as a transport and you want to use WebSockets, you've got to be able to match it up when it comes back. But make sure, pay attention that the ID is not the same when you're setting off the request so that you can match up the responses. Responses can include errors, and a batch will not fail if one of the requests triggers an error. It's just going to return an error object. So now that we know how to make requests via the RPC API, let's look at actually getting data out. So let's start with block data. There are a few similar methods for getting a block, but let's focus on get block by number. If you're going to be ripping the blockchain down to a more usable database, you're going to want to work with a range of blocks. So for params, we're going to specify a block number and the Boolean false, which tells the method to retrieve a particular block, but doesn't want the full transaction in the response. And what I use it for, the transaction itself is pretty useless. The transaction receipt is what I want, so getting all that data is not super helpful. If you find data in the transaction useful, have it come down so you don't have to make a second call. The response has the expected detail data we talked about earlier, but the critical data in the block are the transactions. If you're crawling the chain, you need to know how to get to all the transactions for the block. This is the only way to find them. There is a hierarchical link to the transactions that occur as part of a block. So we're showing a couple here, but likely there's hundreds. These hashes are how we get the transaction receipts. The transaction receipts contain the transaction details accessible by the get transaction receipt by hash method, which takes a single parameter, which is the transaction hash that we had in our block. And the response has the detailed data, but most importantly, the event logs. So now we just need to be able to decipher what's in the logs. So working with log data is a bit more involved than the rest of the blocks and transactions. Encoding hex, decoding hex, pretty simple stuff. Decoding logs require some understanding of the Solidity Application Binary Interface, or ABI. If you're not familiar with Solidity, it's the programming language for smart contracts. Smart contracts emit events to provide externally accessible historical records of what they did in those transactions. The events are stored with separate encoding, which is defined in the ABI specification. So before we get started decoding, we need to understand the anatomy of a log entry. So this is part of a log entry. The pieces not shown relate to the log as far as what transaction is it in, what's the transaction index, what's the log index, what block number, relating it back to the rest of the blockchain. It contains the address of the smart contract that emitted the event. It's not necessarily the address of the contract that was directly interacted with for the transaction, because smart contracts can call other contracts. And then there are topics. So topics are 32-bit values that are added to a logs bloom, which allows you to filter and search. They contain the event signature hash, which allows you to identify which event was triggered. We'll get into more on that in a bit. The indexed event attributes, and the data log attribute contains all the non-indexed event attributes. Again, we'll get into what those mean in a minute. So to read or search the logs, you'll need to know how to encode and decode log topics and data. So depending on how my day is going and the complexity of the logs, I can usually decode log topics and the data I see in block explorers like Etherscan in my head. Fortunately, it's not necessary for my Python code. EthABI, EthHash, EthBloom from the Ethereum project are there to lend a helping hand, and they are the supporting libraries behind Web3Py. So the first item in a log topics array is the event signature hash to identify which event is recorded in this log. The hash is based on the definition in Solidity code. How to derive the hash is defined in the API specification, and it goes like this. Remove all the items and white space besides the name and the parameter types. Generate a Ketchak 256-bit hash of those types, and then you get the resulting signature hash. One thing to always remember is that you can't decode a hash. The event signature is a hash. So you can determine what hash you want to look for, but you can't look through the logs unless you already determined a mapping between hashes and events. You can't decode what event it is. So event signature hashes are useful, but again, you're going to need to know beforehand what you're looking for. The remaining topics are the index parameter values. We can identify those in the event Solidity code definition, right? So there were two index attributes, from and to. The first attribute is from, right? It's an address. We provide the address type to the decode function and the topic value in bytes to the decode method and to get the from address. The two parameters are also an address. And so we perform the same process, right? Passing the type and the bytes to the decode function to get the to address. And that gets us all of the attributes that are indexed. So now we move to the data. The data attribute is comprised of all the non-event attributes. This example has a single 256-bit unsigned integer attribute. All right, it's the one that doesn't have the word index next to it. We pass the list of types, which is just one, the uint256, and we pass it the bytes of the data, and it gets us the value. So now we've been able to decode that, and we can provide the same logic mentally, right? If you were following along, we have a contract, and it performed a transfer from one address to another address of 2 tokens, right? So when I see logs, I've been doing this long enough that that's what I see when I see that, just because I know that 0xDDF25 is transfer 99.999% of the time. So let's get into filtering data. So filters are a common mechanism for the Ethereum RPC API. We're going to look at filtering logs by their topics. If you're not crawling the entire blockchain, if there's a specific set of data you want to look at, or just a specific contract, log filters may be your best bet for getting the data. So let's look at an example. There are a couple ways to filter logs. This example will be the simplest one, the getLogs method. It's a single call, gets you all the data that you need. It needs a starting and end block. Most third-party node providers limit how many blocks a filter can actually filter against. And if you're doing it on your own node, you don't want to destroy the node by searching through almost 16 million blocks on one call. So use the ranges. It optionally requires a contract address. If you want to limit events to one or more contracts, provide those as a string or a list of strings, or a list of addresses, I should say. Otherwise, just don't provide the attribute. And finally, the topics array is the most complicated, but makes sense now that you know how the log topics are structured. We can construct it in the same manner. So for this example, we'll be looking at ERC 721 token burns on the Ethereum name service contract. If you're unfamiliar with ENS, it's the way to translate human readable values into an Ethereum address similar to DNS in the IP networking world. So we're looking, ENS uses ERC 721 tokens, or NFTs, to represent the name registrations. Burning an ENS NFT means the name is no longer registered and can't be resolved as an address. A burnt NFT is defined by specification as the transfer to the 0 address. So we're looking at an arbitrary block range to find log records for ERC 721 transfer events on the ENS contract from any owner to the 0 address. Please note that the order of the topics array is the same order as the transfer event. The ERC transfer event has a third index attribute on token ID, which we're not going to be filtering on. So we can just leave it off because it's the same thing as saying from any. The first step is to translate the data into the necessary format, which is the reverse of what we did, right? To look at the data, we decoded it. To filter it, we're going to encode it. And so we need to encode the 0 address and convert the block numbers into hex. So here's the code to do that, which is super easy, and update the statement. So we're using a from block, a to block, and the ENS contract. And we're going to get the ERC 721 transfer event signature hash, which is the same as the ERC 20 signature hash we already generated earlier. Per the RPC API specification, any translates to null, and update the address with the API encoded value. Now we can build our object, right? So this is a filter object for RPC logs. You can add it into your requests. It's too big to fit on here where you'll be able to see it. So we did it in that manner. We can get the log entries for only the logs that we want this way. So now that we're done with historical data, we're going to focus on state data and smart contracts. We use the ERC 165 interface detection specification for the example. So we're going to check to see, does a specific contract implement the ERC 721 interface? And we're going to be using ethcall for that. And it's how you interact with smart contracts via RPC. And this looks like a lot of information at first glance, but since we're not generating a transaction, we don't need most of the data. So we don't need from, and we won't incur any gas charges, so we don't need that, or transfer cryptocurrency, so we don't need the value, which simplifies things a bit, right? So we just need the to address and the data that's being sent, which is a hash of the function signature and the encoded parameters. So we have a to address on the contract we want to call, which is the ENS example. And then we need to encode the parameters. So the process for generating a function signature hash is very similar to generating an event signature hash. You start with the function definition. You remove everything that's not a function name and parameters, take the remaining parts, and generate a catch-ack hash. And this time you only need the first 4 bytes because that's the way the definition goes. So now that you have the signature hash, you need to encode the function parameters, which is the same thing we did before, right? We identify it by the function. We've got a bytes4 type for the interface ID. We ABI encode the parameter, and we know the value because it's in the RFC. That's a nice little cheat out there that they all, anything that implements 165 tends to put its 165 signature for the interface inside of the definition. We append the hex data to the encoded params and identify the block number. Using latest is how you get it based on the most recent data. So this turns into an RPC request, and we send it to our node, and we get back a result, which we need to decode. So we go back to the definition and figure out what it's supposed to be. So the type is a bool. So we're going to decode the result, passing the result types and the value to the decode function, which comes back the result of true. So this was a lot of information thrown at you very quickly, and I don't expect you to retain much of what I've said. I do hope it has shown you that interacting with the blockchain isn't really that difficult, and getting data out of the blockchain is within reach.
Awesome. Thanks for that, Adam. We've got one question here, which is, just bear with me, let me put it up.
Sure.
Can filtering and parsing data work with Viper instead of Solidity?
So it doesn't necessarily matter, right? Because it's the bytecode. So when you're dealing with what's inside of the system, it's dealing with bytecode. So Solidity compiles onto bytecode, and my understanding of Viper, which is limited, is that it's just compiling down to the same bytecode that you get, which is what the ABI specification is, right? That's the application binary interface. So when you're doing filtering, you're filtering on the data. So all you're caring about is that you're giving it the right information. So when you take that definition, that ABI definition of the function, it's going to have to work. Now, if you're looking at a Python definition, it's going to not have the same attributes. So you're going to have to figure out a way to translate that into, because there is no uint 256, right, type in Python. So you would have to convert that when you're doing the encoding, but the encoding library is what's going to do that for you for the most part. So it needs to know what it's going to be on the other side. So if you can derive that information to determine things like the function hash or the event hash, right, because that's what you're specifically looking in filtering the events. If you can get the event hash, you can get there. You just need to know what your Python code and Viper is being translated into in the bytecode. And I hope that answered the question.